Sample exam 2. Problem number 1. Find the following limit, if it exists, or show that the limit does not exist. Okay, so I'm going to look at the following. Well, I'll let I'll look along the path where x is equal to, let's say, ky squared. And so if I let f of xy equal x squared, xy squared, cosine y over x squared plus y to the fourth. Okay. Then the limit, I'm going to look at the limit as, let's say y goes to 0 of f of ky squared. Y. Okay. So I'll look at that limit. So I'm just going to go along one particular path. Let me add a little bit more room here to do it. And so this is the limit. As y goes to 0 of x y squared cosine y over x squared plus y to the fourth. And so now everything's going to have a y to the fourth power in it. And that's what I was attempting to do. So now this is a limit as y goes to 0. Let me write this as y to the fourth. Actually, I'll just write it as k y to the fourth cosine y over, factor out y to the fourth, so this is y to the fourth times k squared plus 1. So the y to the fourths cancel. And so this is just equal to the limit as y goes to 0 of k cosine y over k squared plus 1. As y goes to 0, this approaches k over k squared plus 1. But of course, for differing values of k, you'll get differing values of this limit. So therefore, this limit does not exist. The limit as xy approaches 0, 0 of xy squared cosine y over x squared plus y to the fourth. This limit here does not exist. So, actually, let me, since I have more room here, so that is my answer. Okay, let me do problem number 2. Find the following limit, if it exists, or show that the limit does not exist. And so in this case, the limit should exist. It should be 0. Just by looking at what it looks like. So why don't we do the following? So again, let's call f of x y x cubed plus y cubed over x squared plus y squared. Okay. And so now let's look at the limit as r goes to 0 of f of r cosine theta, oops, r sine theta. Okay, so let's look at that limit. So this is a limit as r goes to 0 of r cubed cosine cubed theta plus r cubed sine cubed theta over r squared cosine squared plus r squared sine squared. Well, maybe I'll just write it like that. Let me give a little bit more room here. So I can factor out r cubed from the numerator to get cosine cubed plus sine cubed. And while factoring out r squared, I get cosine squared plus sine squared, but cosine squared plus sine squared is just 1. And so let's cancel out 2 of the r's. And so I just get the limit as r goes to 0 of r times cosine cubed theta plus sine cubed theta. Well, cosine cubed plus sine cubed is bounded. It's certainly less than 2 in absolute value. And so as r goes to 0, well, something going to 0 times something that's bounded will go to 0. Or you can use the squeeze theorem. This is bounded between plus and minus 2r. And as r goes to 0, this both 2r and negative 2r go to 0. Therefore, this limit here is 0. And so we have that the limit that this limit here, actually, maybe I'll just copy it, that this limit is equal to 0. And that's your answer. Okay. So let's do problem number 3. It says, let me move this up. Now the 0, 0 looks a little weird, but okay, so determine whether the second partial derivatives for the following function are continuous at the origin. Actually, maybe I'll slightly modify so it looks better at the point 0, 0. So now it doesn't look like it's just hanging, the 0, 0 is just hanging there. Okay, so let's do that. So I have to find the second partials. Okay. So first, and you want to only do it at the origin. So let's do the first partials. So to do the second partials, I'm going to have to partial f at x0, 0y, and a mixed partial weight. Well, it still have to be that. Okay. Oh, but it could be a, okay, so let's determine the partial of f with respect to x at x 0. Okay. So that's equal to, so I'll have to at least figure out that in order to look at some mixed partials at the origin. So this is equal to limit as, let's say, h goes to 0 of f of x plus h 0 minus f of x 0 all divided by h. So this is a limit as h goes to 0. Well, let me get some more space in here. Actually, I know that at 0, if I plug in y equals 0, I'll just get 0, but I guess I should show that. This is the limit. As h approaches 0 of, so this is x cubed y minus xy cubed over x squared plus y squared. Okay, so that's it. That's what this is equal to. Of course, I noticed that no matter what, we can assume that h here is not equal to minus x for any of the x's. Just change it if it is, so that I can assume that this term is not 0. Minus f of x 0. Well, x 0 is going to be the same thing, so the x maybe I'll minus x 0 cubed over x squared plus 0 squared. All divided by h. But of course, this is 0. Everything's multiplied by 0. Divided by x plus h squared is 0. This is 0 in the numerator. Divided by x squared is 0. And so I'm just taking the limit as h approaches 0 of 0, which of course will be 0. Okay. So that's a partial of x at partial of f with respect to x at x 0. Let's look at the partial of f. With respect to y. So this is the limit. As k goes to 0. F of 0 y plus k minus f of 0y over k. And again, I can assume that k is such that, well, oh, what if y is 0? Okay. Oh, it doesn't matter if, because that gave 0 anyway. So in either case, that's going to be, this term will be 0. Okay, so this is equal to, I guess I'll need some more room. Oops. I accidentally put in the wrong location. So let's get some more room here. Okay. So this is equal to the limit as k approaches 0. Of, well, plug in 0 for x. X plus k, y plus k, minus, plug in 0, and then y plus k cubed over plug in 0 and plug in y plus k minus let's plug in 0. This is assuming that y is not 0, but then in the next line, no matter what, it's going to be the same thing. So 0 cubed times y minus 0 y cubed over x squared plus y squared, all divided by k. So this is equal to well, the first term is 0. The second term is 0. And this is assuming that y is not 0, but if y is 0, then f of 0, 0 is 0 also. So this is still 0 over k. So for the second part here, if y is 0, we can go directly to here. If y is not 0, then we do this intermediate step and still get here. But no matter what y is, this is still a true statement here, because we can assume that k is such that y plus k is not 0. Because take the limit is k goes to 0, and you can assume that it has a differing value. So this is just 0. The limit as k goes to 0, 0 is 0. Okay. Next. Let's see. Will I need to do the other one? Well, let's just check. Okay, so now let's look at the, will I be able to get all the second partials? Let me just check. So that will be, so if you do 0, 0, that'll be the partial at h minus 0, 0. Oh, did I do? The partial at 0, 0. Oh, so that's right. So now I have actually done the partial at 0, 0. Okay, so that's good. Okay, so I can at least find the second partials of those. Now let's see the mixed partials. So partial f of x, y. So it'll be some limit. Zero k. So we'll have to do the 0 and the k on the other side. Okay, so I need one more. I need two more. Okay, so I need the partial of f with respect to x of 0, y. Because I did x 0. Okay. So now let's see what this is. This is the limit as h goes to 0 of f of h, y minus f of 0, y over h. I'm trying to do this without taking the partials. I may have to take the partials, but okay. Oh, you know what? I have to do the second, I have to show the second partial is continuous at 0, not just its value at 0. Okay, but so far so good. These are fine things that I've shown so far. Let's take so these are things I need to know anyway. But let's take the partial of f with respect to x. Let's actually have to take that real partial derivative. And let's assume that we're not here at the origin. So let's do this, assuming here that x squared plus y squared is, well, assuming that xy is not 0, 0. So let's make that assumption. So let's take the partial of f with respect to x. I guess I have to do this no matter what. So the derivative of the numerator so the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, all divided by the denominator squared. Okay, so let me just check that I did this correctly. So the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. Okay. So let's multiply this out. So let's multiply this and everything by minus 2x. Okay, so this is equal to 3x4y plus 3x squared y cubed minus x squared y cubed minus y to the fifth, multiply everything by minus 2x, minus 2x to the 4y plus 2x squared y cubed over x squared plus y squared to the fourth, squared. So this is equal to, things are probably going to cancel. Let's see, or at least combine y4, x4y. So this is equal to 3x to the fourth y minus 2x to the fourth y is x to the 4y. 3x squared y cubed minus x squared y cubed plus 2x squared y cubed is 4x squared y cubed. That's 6 minus 2 is, wait, let me, 2. So that's minus, wait. Oh, that's this one. So it's 2 plus 2, yes. So combining these, you get 2 of these plus 2 more is 4. Minus y to the fifth. And this was combined with that one. And over x squared plus y squared to the fourth. Okay. So that's the first partial. Let's look here at the second partial. Let's look here at the other first partial, sorry. The partial of f with respect to y. Okay. And so let's take the partial. And so take the derivative of the numerator, just using quotient rule. Times the denominator minus, so it's x cubed minus 3xy squared. Okay, minus the numerator, x cubed y minus xy cubed times the derivative of the denominator, 2y, all divided by the denominator squared. Squared. Why did that raise to the fourth power? Okay, so that's squared. I take the second partial will be the fourth. Okay, so that's squared. Okay. And so this is equal to multiply x cubed negative 3xy squared inside the parentheses, multiply negative 2y inside the parentheses. So I get x to the fifth plus x cubed y squared minus 3x cubed y squared minus 3x y to the fourth minus 2x to the third y squared. Minus and minus become a plus 2x y to the 4, all divided by your denominator squared. So this is equal to x to the 5. There's a x cubed y squared minus 3 of these x cubed y squared minus 2 of them, x cubed y squared, so that's minus 4 x cubed y squared minus 3 xy to the fourth plus 2 of them is minus x y to the 4 divided by x squared plus y squared squared. Okay. Okay. So let me try to simplify that. So this is equal to, oh, of course, I should say that, again, I'm making the assumption just like before, that x, we're not at the origin. We already did the origin and showed that that was 0, so that was fine. So this is equal to, okay, so that's equal to that. Okay. So we have the following. I've shown that the partial of f respect to x, that this is going to equal okay. So that was x. If we're not at the origin. And we showed that it was 0 if we were at the origin. We actually showed a little bit more. So we showed that if x were 0, that this was 0. Okay, and we've also shown that the partial of f with respect to y that this partial is, there it is right there. This is if we're not at the origin. And we showed otherwise it was 0 at the origin. Okay. So now let's take the second partials. Let's say the partial okay, so let's take this second partial here. And I guess let's do this. Oh, so I didn't really need that if I can show this. So let's do this for cases where we're not at the origin. This is, so I can take the partial with respect to x. Okay, so if I do that, that's derivative of the numerator. Oh boy, this is going to be a long one. Okay, so the derivative of the numerator, 4x cubed y plus 8xy cubed. Oh, then that's 0. So derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. So I'll bring down the 2 times, this is the first power, times the derivative of what's inside. So 2 times 2, let's make that a 4x. All divided by the denominator squared. Okay. By the denominator squared. So this is equal, don't have any room. Okay, so let's get some more space here. This is equal to, let's get rid of one of the x squares. So this becomes x cubed. Okay. So this becomes 3. Okay, so this is equal to, and now let's multiply this out. So this is 4x to the 5th y plus 4x cubed y cubed plus 8x cubed y cubed plus 8xy to the fifth minus, multiply negative 4x inside the parentheses. So negative 4 y, negative 16, 4 and 4 is 16, x cube, y cube, minus and minus is a plus 4xy to the fifth, all divided by x squared plus y squared cubed. Okay, so let's see what we have. So x to the fifth cancels. So I have some cancellation here. 4x to the fifth y cancels. Okay. X cubed. Let's see if anything else cancels. X cubed doesn't quite cancel. Okay, so I have here 4. Oh, well, let's do this guy here. I have an 8xy to the fifth plus 4xy to the fifth is 12 xy to the fifth. Then I have the rest of them are x cubed terms, x cubed y cubed terms. So I have a 4x cubed y cubed, 8x cubed y cubed minus 16x cubed y cubed. So that's 4 plus 8 is 12 minus 16 is a negative 4x cubed y cubed over x squared plus y squared to the power of 3. Okay. Let's do some further mixed partials. And then I'll show that these don't exist. Partial f respect to x. Oh, let's do y then x. Partial y, partial x. Okay. So let's take the, and again, let's assume that we're not here at the origin. Assume that we're not at the origin. Okay. And so let's take the partial of this with respect to y. And so this is going to be derivative of the numerator, x4 minus, no, actually that one was a plus. The minus is the last one. That's a plus and that's a minus. Okay, so plus, plus 12 x squared y squared minus 5 y to the fourth. Derivative of the numerator times the denominator, x squared plus y squared squared, minus the numerator, derivative minus the numerator, x4y plus 4x squared y cubed minus y to the fifth times the derivative of the denominator. Again, this will be bring down to 2 times x squared plus y squared to the first times the derivative of what's inside, which is a 2y, so that becomes a 4y. All divided by my denominator squared. And so I can cancel out one of these, and I'll have 3 remaining. Okay. Multiply everything by x squared. So that becomes x plus 12x4 y squared minus 5 x squared y4. Multiply everything now by y square, x4 y square plus 12x2 y4 minus 5 y6. Multiply everything by negative 4y, negative 4x4 y2, negative 16 x 2y4 minus and minus is a plus 4y6, all divided by x squared plus 3. So this is equal to x to the 6, 12 x4 y squared plus x squared y squared, that'll be 13 minus 4 x4 y squared minus 5 x squared y squared. Start over again. Minus 5 x squared y4 plus 12 x squared y4 is 7 minus 16 x squared y4. So that gives you a minus 9 x squared y to the 4. Okay, so I already have the x4, y2, x2, y4. I don't have a y6. So minus 5y6 plus 4y6 is minus y to the 6. I already did x4, y2, 2, 4, so that's it. Divided by x squared plus y squared to the power 3. Okay. Let's do so now let's do so I had both mixed partials, right? No, I haven't done the other mixed partial. Okay, so let's do another mixed partial. So I need x, y. Partial. Watch that be this one I just did. Yep, I did yx. I want xy. Okay, so I want x, y. Now I'm going to take the partial derivative with respect to x of the partial derivative of respect to y. Okay, so let's do that. So let's take the derivative of the numerator, 5x4 minus 12x2 y2 minus y4 times the denominator, x squared plus y squared. Squared minus the numerator, x5 minus 4 x3 y2 minus xy4 times the derivative of the denominator, bring down the 2, x squared plus y squared, times the derivative of what's inside. So that'll give me a 4x. All divided by squared. So I can cancel out one of these, x squared plus y squares. That'll give me a cube in the bottom. Multiply. So multiply everything here by x squared, 5x6 minus 12x4 y2 minus x2 y4 plus, multiply everything by y2, 5x4 y2 minus 12x2 y4 minus y6. Multiply everything by negative 4x, negative 4 x6 plus 16x 4y2 plus 4x2 y4 divided by x2 plus y2 cubed. So this is equal to, okay, combine like terms. Five x to the 6 minus 12 plus 5 is minus 7 plus 16 is plus 9 x4 y2 minus x2 y4. So that gives you minus another 12 is minus 13 plus 4 is minus 9 x2 y4. So 4, 2, and 2, 4. So y6. All the other ones are gone. Divided by x squared plus y cube plus y squared cubed. Okay. And lastly, I just need the partial with respect to y. Okay, so now I just do second partial of f with respect to y. Okay, so I'll just be taking the partial of y with respect to y. So the derivative of the numerator, Wait, I already forgot. I already forgot the partial with respect to y. Oh, so that'll give you a 0. So partial of this respect to y. Okay, that's 0. That's a okay. Got it. And so the partial of the numerator minus 8x 3y minus 4xy3 times x squared plus y squared squared minus, that was the 5, x5 minus 4 x3 y2 minus xy4 times the derivative of the denominator. So I'll bring down the 2 times x squared plus y squared to the first times the derivative of what's inside. So a 2 times 2y is 4y. All divided by the denominator squared. So this is equal to, cancel out one of these x squared plus y squares. And so you get, multiplying everything by x squared, I get a negative 8 x5y minus 4 x3 y3, multiply everything by y squared, minus y3 minus 4x y5, multiply everything by negative 4y, so minus 4x5y plus 16x3y3 plus 4xy5 divided by x squared plus y squared cubed. Okay, good. So I guess I had to actually do these computations. So this is equal to that's a 5-1. That's at negative 8 x to the 5 y minus 4 x to the 5 negative 12 x4 y minus 4 minus 12. Okay, so I have 16x cubed y cubed minus 4x cubed y cubed minus 8x cubed y cubed. That's 16 minus 12 is 4 x cubed y cubed. And then I have minus 4 of these. And plus 4 of those. So these cancel. And then, oh, isn't that x to the 5th? That's an x to the 5th y. I had minus 8 of them minus 4 of them. And that's it. So I take care of all terms over x squared plus y squared cubed. Okay, so those are all the mixed partials. So now, after I've computed them, I want to show that that they're not continuous. Okay, so let me. Now I've forgotten what it was equal to. Okay, so that's. I'm going to show this is not continuous. at the origin. Okay. So in all these, I'm assuming, oh, I see, somehow I didn't, oh, when I made that, okay, all these, I'm assuming that I'm not at the origin. I said that explicitly here, here, here. For this last one, I didn't. So let me just explicitly state that. So that's a reason to move this guy down. Okay, so let's state this, that I'm making this assumption. Okay, so now let's see what happens at the origin. So let's take the second partial of f with respect to x. Okay. And so let's try to see what that is. Well, let's do the following. Let's do the limit as x goes to 0, let's say, of the partial of f with respect to x. And let's do it along some path. And I think this should work. Okay, so that was so that would make those all 6 powers. Okay. Just for 1 second, let me leave that there. And so I can see this is the limit. As k goes to 0. Of partial f, partial x. Well, let's just plug it in. Of (12) x k x to the 5 minus 4 x to the 3 kx to the 3 over x squared plus k squared x squared cube. Okay. So this is equal to the limit as k goes to 0 of 12, k to the 5, x to the 6, minus 4, k to the 3rd, x to the 6, over. Factor out x squared, so that's x to the 6, 1 plus k squared cubed. Okay, so I can cancel out the x to the 6's. Oops. So is equal to the limit as k goes. Why is k going to 0? Why is k going to 0? Why is k going to 0? So here, I guess I'm assuming k is not 0. Okay, that looks better. And so this is minus 4k cubed over 1 plus k squared cubed. Well, as x goes to 0, this just goes to this value. And so this has differing values depending on what k is. And so this says that this limit doesn't exist. And so the limit as you approach the origin, the second partial, that this limit here does not exist. Okay. Let's look at the other mixed partial. So that was the second. This one. So let's look at another mixed partial. So this is yx. So yx. Okay, so let's do yx. So let's look at that. And again, let's do the same sort of limit. So just like what we did here, we'll take the limit as x goes to 0. And let's do kx. I did that for yx. Okay. So this is the limit as x goes to 0. Of x to the 6 plus 9. I'll just put it out. K squared x to the 4th times x squared minus 9 x squared. This will be y to xy to the 4th, so that's k to the 4th, x to the 4th, minus, well, kx to the 6th is k to the 6th, x to the 6th, divided by x squared plus k squared x squared cubed. So do the same thing. So this is a limit as x goes to 0. Let's factor out x to the 6th. What remains is 1 plus 9k minus 9k squared minus 9k to the 4 minus k to the 6 over, factor out x squared, so it's x to the 6, 1 plus k squared cubed. And so the x to the 6 cancel. This is just now equal to a constant. And so as x goes to 0, this constant just remains the same. But this constant here is different for differing values of k. And so that implies that this second partial, now I forgot, it was xy. It was yx. That this does not exist. Okay. So that doesn't exist. Checking what else we do. Since this is so long, I have to check what the question is asking me now. The following are not continuous. So certainly the second partials are not continuous because they don't even exist at the origin. Okay, so I did those first two. I didn't do xy yet. Oh, I should have done xy. So I didn't do xy yet. So let's do xy. We can limit as x approaches 0. Of f of partial So second partial of f with respect to x, y of x, k of x. Okay, so I need another page. So this is the limit. Oops, of course. I'm just taking x going to 0. And so the limit there and doesn't, well, that's both, this limit doesn't exist. I should say it that way. At this limit doesn't exist. Because that's actually what I showed. Okay, so now this is equal to limit as x approaches 0 of this thing I bet you I didn't copy the other guy because that looks the same. So this is going to be xy. xy. Are the mixed partials the same? The mixed partials are the same. Yeah, those are the same. So I don't need to show that because the mixed partials are the same. So if one doesn't, obviously, if they're the same, then this limit doesn't exist for the other one. And since the limit from one of them didn't exist, then the other limit didn't exist. And so the limit, because obviously the calculation would be the same, the partial x, y, that this doesn't exist. So I just have one more to do. And so let's just do the limit as x goes to 0, partial f respect to y at x, kx. Okay, so let's just do that last one. So the second partial respect to y is that? And that doesn't look continuous either. Okay, so let's do this. So this is the limit as x goes to 0 of negative 12 x to the 5th kx plus 4 x to the 3rd kx cube over x squared plus k squared x squared cube. Okay, so let's simplify that. So this is equal to the limit as x goes to 0 of, let's factor out x to the 6th, negative 12 k plus 4 k cube divided by x to the 6th, 1 plus k squared cubed. So this is the limit as x goes to 0 of negative 12 k plus 4 k cube for 1 plus k squared cubed. Insert. So this is equal to, well, it's a constant, so it's just equal to the constant, negative 12k plus 4k cubed over 1 plus k squared cubed. So this implies that the limit as xy goes to 0 of the second partial with respect to y does not exist. So therefore, none of these mixed partials can be continuous. They don't even exist at the origin. And so this implies that the second partial so if the limit doesn't exist, then it is not continuous at that point. And so none of these partial derivatives are continuous at the origin. Okay. Let me do problem number 4. Use differentials to estimate the amount of 10 in a closed 10 can with diameter 8 centimeters and height 12 centimeters if the 10 is 0.04 centimeters thick. So I have some cylindrical can, And I know that the volume is pi r squared h. I want to determine, well, to approximate the thickness of this can. So it's the change between this and, well, a little thickness to it. Okay. And so the diameter, so that says that its radius is 4. The height is given as 12 centimeters. And well, we're going to a little bit thicker. And so we're going to change this radius by 0.04 centimeters. And well, then its height is going to be raised by both on the top and bottom, because it's a closed can, by 0.04. So the change in the height will be 0.08 centimeters. So I have V equals pi r squared h. So dV is equal to, well, the derivative of r squared will give me a 2 pi r h dr. Derivative of a differential of h will give me a pi r squared dh. And so dV is 2 pi r h 12 dr 0.04 r 4 dh 0.08. Well, let's do 0.08. And so dV is equal to 0.16 times 12 times 24 gives me 3.84 pi. 16 times 0.08, 1.28 pi. So dV is 45.12 pi. And so the thickness of your can is approximately 5.12 pi cubic centimeters. Okay. And so that is the amount of 10 that is used to make this tin can. It's approximately 512. Well, 5. Oh, and maybe I'll do a slight this is an approximation anyway, but so this is approximately 5.12 times pi is around 16 point, let's say 0.8, around 16 cubic centimeters. Okay. So it's approximately that much. Let me do problem number 5. So use the definition derivative to show that the following function is differentiable everywhere. Okay, so I want to somehow look at, and let's do it everywhere. Let's say xy, that this is equal to df, let's say at xy, plus some little o of h. Okay. So little o of that. Okay, so well, delta f and so this is just a change in f. So this is f of x plus h y plus k y. So this is equal to x plus h squared y plus k squared minus, well, this is x squared plus y squared. So let's multiply this out. So we get x squared plus 2xh plus h squared plus y squared plus 2yk plus k squared minus x squared minus y squared. So some things are going to cancel. The x squares and the y squares cancel. So this is equal to 2xh plus 2yk plus h squared plus k squared. And so this is equal to, well, I can write this as the dot product of 2x, 2y with hk plus this last term, h squared plus k squared. And maybe I'll write this as this squared. Okay. Well, I should note that if I let d equal this dot product, then this is a linear transformation. The matrix representation is just the vector 2x, 2y. Okay. And this last term here is O, little o. Of h, okay. Since if you divide this by the square root, since the limit as hk goes to 0, of this guy, well, maybe I'll just write, yeah. Divided by the length of this, which is the limit as hk goes to 0 of the square root over the square root. And so this is just going to be 0. So this is one square roots cancel, so you just get h squared plus k squared. So this is 0. And therefore it's a little low. And so I have something plus O, and this something is a linear transformation. So the matrix representation. So F is differentiable. At any point xy, and it has matrix representation of 2x, 2y. And that's what I wanted to show. That it's differentiable. Okay. It's 1 o'clock. I'll show this here. Oops. Let's go down. Show that both partials exist at the origin for the following function, yet the function is okay. So let's do that. So let's take the partial of f with respect to x at the origin. So this is the limit as h approaches 0 of f of 0 plus h Maybe I'll just write that. Minus f of 0, 0 over h. So this is the limit. As h goes to 0, I'll leave it a little bit more space. Limit as h goes to 0 of, I don't like that. Plug in h, 0, h, 0, and f of 0, 0, 0, all over h. Well, each of these are going to be 0. Okay. Okay, let's see what it's doing here. Good. Okay. So each of these quantities in the numerator. So this will be 0 divided by h squared is 0. 0 minus 0 is 0. The limit of a constant is just that constant. So we have that it's equal to 0. So the limit exists. Let's do the other partial. So this is the partial of f with respect to y at the origin. And so if I do that, this is the limit as k goes to 0, f of 0, 0 plus k, minus f of 0, 0, over k. So this is equal to limit, need more space, limit as k goes to 0. This was xy. So xy, x, y, over x squared plus y squared minus f of 0, 0, which is 0, over k. This is the limit as k goes to 0. Each of these quantities are 0. And so this is just a constant 0. Limit as k goes to 0 for constant is just the constant. Okay. And so both the partial derivatives exist. Of x, f of y exist at the origin. And is equal to 0, actually. So now let's see if this function is differentiable. Okay, well, if f were differentiable, at the origin, then delta f, then there exists a linear transformation df with, say, matrix representation AB such that, okay, delta f at the origin of HK is equal to df at the origin HK plus the low of HK. Which is, well, the dot product between these two vectors. It's the matrix multiplication of these. And so this would be AH plus BK. And so I have and, well, delta F and 0, 0. HK. This is F of 0 plus H, 0 plus K, minus F of 0, 0. And I have this. So this is equal to HK and then 0. Okay. So it's HK over X squared plus Y X squared plus okay, so this is equal to hk over h squared plus k squared minus f of 0, 0, which is 0. So this is hk over h squared plus k squared. And so we want that the limit as hk goes to the origin of, well, no, I should say this first. So this says that hk over h squared plus k squared has to equal ah plus bk plus the low of this h squared plus k squared. And so this says that we must have that the limit as hk goes to the origin of hk over h squared plus k squared minus the ah plus bk, that if I divide this by h squared plus k squared, that this must equal 0. And so it says that this limit here let's multiply, let's say, by x squared plus k squared. So this is xh minus ah plus bk h squared plus k squared over h squared plus k squared to 3/2. It must be that this limit is 0. So the only way for this derivative to exist is if this is 0. And this is a cube. Okay, so, and that's a cube. So this is, so this is, let's look at let's look at some sort of limit here as h goes to 0 of, let k I'm going to let K here equal CH. And so H, CH minus AH plus B, CH, H squared plus C squared H squared over H squared plus C squared H squared to the 3/2. This is equal to the limit as H approaches 0. Let's factor out H squared. What remains is C minus AH plus, maybe I'll put the H out here, minus H, A plus BC times 1 plus C squared over, factor out an H squared, so it's H cubed 1 plus C squared to the 3/2. Okay, so this is equal to, I can cancel out 2 of these. So this is the limit as H approaches 0 of C minus H, A plus BC, 1 plus C squared over H, 1 plus C squared to the 3/2. Well, as H goes to 0, this numerator is just going to go to C. The denominator will go to, well, 0 times this constant. So this whole thing goes off to, well, infinity. It doesn't exist. Okay. And it was supposed to equal 0. So whatever. It doesn't go to 0. Infinity, depending on the sign of C, and so this doesn't exist. So therefore, my assumption that it must equal 0 is false. It's not equal to 0. Therefore, there doesn't exist a linear transformation that satisfies this. So therefore, this function is not differentiable. So this implies that there is no such linear transformation. It means that f is not differentiable at the origin. And that's what we wanted to show. So, even though the partials existed, they were both equal to 0. We still had that the function was not differentiable. So I have here a sphere, and we want to find the box that has maximal volume. And so let's use the following notation. So let the length of one side be, well, 2x, width 2y, and height 2z. So that means that from the center, we just go x, then y, then z. And so I want to maximize the volume, which is length times width times of the rectangular box. So the volume is length times width times height. And the equation of a sphere is such that, well, if you're at any point, then the length in x plus the length in y plus the length in z square, the sum of those squares should equal the square of the radius. So in this case, the way I've set this up, x squared plus y squared plus z squared equals r squared. Now, I'm going to do this, I guess, two different ways. The first way is to reduce this to a different problem. So what I'll do is I'll have to make some assumption. Okay, so I'll have to assume that x is greater than 0, y is greater than 0, and z is greater than 0, in which case x, y, and z all between 0 and r, so that I can solve for one of the variables, let's say z, in terms of r and x and y. So I have that z squared equals r squared minus x squared minus y squared. And so z is equal to plus or minus the square root of r squared minus x squared minus y squared. And we can take it to be plus because I've assumed that z here is greater than or equal to 0. So now I want to maximize the following function. And in this case, the function will only be a function of two variables, x and y. It'll be 8x y times z rad r squared minus x squared minus z squared. Minus y squared. So I want to maximize this. And so let's find the critical values for this function. And then let's look at the Hessian and see if it's positive definite. And so, because we want to maximize this function. Okay, so let's take the partial of v with respect to x. I'll just use the product rule. So the derivative of the first, 8y, times the second, rad r squared minus x squared minus y squared, plus the second, plus the first, 8xy, times the derivative of the second. So the derivative of r squared minus x squared minus y squared to the 1/2. Well, you bring down the 1/2. You subtract 1 from the exponent. and then take the derivative of what's inside minus 2x. And so this is equal to getting a common denominator of rad r squared minus x squared minus y squared. So let's multiply and divide this first term by that. So I get an 8y r squared minus x squared minus y squared minus the 2 cancels. So I get a minus 8x squared y. Oops. Minus 8x squared y. So this becomes actually, that's right. This is partial phi, partial x. This is just going to equal 8 r squared y minus 8 x squared y minus another 8 gives you minus 16 x squared y minus 8 y cubed over rad r squared minus x squared minus y squared. So lastly, let me write this as partial. Okay, let's try this again. Partial v with respect to x let's factor out an 8y. So we get r squared minus 2x squared minus y over rad r squared minus x squared minus y squared. Okay. Let's take the partial with respect to y. And so this is equal to, let me just be sure I have it correctly. Of course, it doesn't do that. Let me copy this for 1 second, just to be sure that I'm taking the correct partial. Good. So this is equal to, and that's other stuff. Okay. So take the partial with respect, so again, let's use the product rule, Leibniz rule. So the derivative of the first times the second plus the first times the derivative of the second, r squared minus x squared minus y squared. Let's bring down the exponent. Subtract 1 from the exponent times the derivative of what's inside. And so the partial of v with respect to y is getting a common denominator, rad r squared minus x squared minus y squared. So we're going to be dividing each of these by that. So let's multiply and divide by rad r squared minus x squared minus y squared. So you get 8x. And let's multiply the 8x inside the parentheses. R squared minus 8x cubed minus 8x y squared minus, again, the 2's cancel. And so I get a minus 8. Okay, let's do this. 8xy squared. So this is equal to 8 xr squared minus 8x cubed minus 16 xy squared over rad r squared minus x squared minus y squared. So let's factor the numerator, make it this look a little bit easier. So again, I'm dividing by r squared minus x squared minus y squared. And so let's factor out 8x. What remains is r squared minus x squared minus 2y squared. Okay, good. Let's set each of these equal to 0. Yeah, I need more room here. Define the critical numbers. So let's determine first critical numbers. Okay, so let's set the first partial with respect to x equal to 0. And so let's set 8y r squared minus 2x squared minus y equal to 0. And let's also set r squared minus x squared minus y squared equal to 0. Note, this would say that x squared plus y squared equals r squared, in which case that would say that z, well, maybe I'll just, this would imply that z equals 0, which would imply that the volume would equal 0. So I know that that's not going to be a maximum. So this is certainly not going to be a maximal point here. So let's set each of these equal to 0. Critical numbers for the maximum. Okay, because I'm going to be getting rid of some other points here, some other critical numbers. So notice in this case, y equals 0. But again, if y equals 0, the volume is 0. So I'm going to get rid of this point. So I'm going to get rid of these, because if we have a maximal volume, the maximum volume is going to be greater than 0 by our assumptions. Otherwise, the function would always be 0 because at the boundary it's 0. Okay, so I have here that y equals 2x squared minus r squared. Okay. Next, let's look at the other partial. Ooh, wait 1 second. That's a squared. That was an error. That was an error. Okay, sorry, that was an error. I had that y squared. This was a y squared. Okay, sorry, that's y squared. So it should be in this case that y squared plus 2x squared is r squared. Okay, so I have that instead. Okay, so let's try to find the other conditions for this. So I also have that the partial with respect to y, so 8x r squared minus x squared minus 2y squared. That's 0. Or the r squared minus x squared minus y squared is 0. But again, this would say that z equals 0. The volume would be 0. So again, that's not going to be maximal. Here I have 8x equals 0, or r squared minus x squared minus 2y squared equals 0. But in this case, x equals 0. But again, that would say that the volume is 0. And so that's a contradiction. That can't be a maximal value. And from here, I have that x squared plus 2y squared equals r squared. Okay, so I have x squared plus 2y squared equals r squared, and 2x squared plus y squared equals r squared. Okay, so let's multiply this by minus 2 and add. And so I get minus 4x squared minus x squared is minus 3x squared. The y squares cancel, equals r squared minus 2r squared is a minus r squared. So I get that x squared is equal to 1/3 r squared. Since I want that x is greater than 0, well, greater than or equal to 0, then I have here that x is r over rad 3. But if x is r over rad 3, then I have, well, x squared, r squared over 3, plus 2y squared equals r squared. And so I get that 2y squared equals r squared minus r squared. And so I have here that y squared equals 1/3 r squared. Again, I'm assuming here that r is greater than or equal to 0. And so that y here is greater than or equal to 0. So I have that y is equal to r over rad 3. Okay. And so I have that the critical number is r over rad 3. Okay, 1 second. See what happens. R over rad 3. R over rad 3. So let's look at the, and this is where the gradient is 0. So since this is where the gradient is 0, I can actually use the second derivative test. So now let's use the second derivative test. So in order to use the second derivative test, well, I'm going to have to look at the Hessian. So let's do that. So let's take the partial of v with respect to x. One second, let's see what the partial of v with respect to x is. This guy. Just want to be sure. Actually, this. So let's take the partial, let's use the quotient rule. So let's take the derivative of the numerator. So 0, this will be a minus 32xy minus 0 times the denominator minus the numerator, 8 r squared y minus 16 x squared y minus 8y cubed times the derivative of the denominator, So I'll bring down the exponent. Subtract 1 from the exponent. Times the derivative of what's inside respect to x. Minus 2x. All divided by the denominator squared. And so this is equal to multiply by r squared minus x squared minus y squared to the 1/2. So I get a minus 32 xy times r squared minus x squared minus y squared minus 8r squared y, 16x squared y, 8y cubed, cancel, times minus x. All divided by this r squared minus x squared minus y squared to the 3/2. Let's plug in. R over rad 3. So the critical value was r over rad 3, comma r over rad 3. So x times y just becomes r squared over 3. And so each of these are r squared over 3. So that's the whole thing is just going to be an r squared over 3. Once I subtract these two out. Minus and minus make this a plus. So this is going to be xy, which will again give me a r squared over 3 plus x cubed y. Well, that's like something to the 4th. So that's r to the 4th over 9. Plus, oh, this is again going to be a y cubed times x, and these are all r over rad 3, so that'll give you r over rad 3 to the 4th. So that's plus, minus, that's a minus. And why is that a plus there? Here, wait. Let's give you a minus. 8 r cubed over r to the 4th over 9 divided by maybe I'll still just write this as r squared minus r cubed, r squared over 3 r squared over 3 to 3/2. So this is equal to not 3. So r squared minus, well, r squared over 3 and r squared over 3 is a 2r squared over 3. And so r squared minus the 2r squared over 3 is r squared over 3. So this becomes minus 32 r to the 4th over 9 plus, that's an r to the, oh, that's r squared, yeah. That's a plus 8 r to the 4th over 3 minus 16 r to the 4th over 9. We'll get a whole bunch of the same things. Minus 8 r to the 4th over 9 divided by, well, again, r squared minus r squared over 3 minus r squared over 3 is r squared over 3. Three halves. So this is equal to let's get that a little bit better. Okay, so let's bring a r to the 4th over 9 out. So this is r to the 4th over 9 times minus 32 plus 24 minus 16 minus 8 divided by r to the 3 halves, r squared to the 3 halves is r cubed. So I have an r cubed. Divided by, so let's bring this on the top, 3 to the 3 halves. Yeah, well, let's try as 3 to 3 halves. And so I just get an r. And if I divide by 3, I get a 3 here and a 3 to the 1/2 here. So this is equal to r. I'll give you 24. The 24, the 16, the 8, they cancel. So that's a minus 32. Minus 32 r rad 3. So after all the cancellations, that's what you get. Okay. Let's take the partial of v respect to y. Okay. So I need some more room here. Let's see if I can get back control. Okay. Let's see if I can get back control for a second. Okay. Let me just copy this just to be sure I have it correctly. Okay. Let's take the partial of this with respect to y. And so you'll get an 8. Again, I'm going to use the quotient rule. So it's 8 r squared minus 16 x squared minus 24 y squared times the denominator, r squared minus x squared minus y squared to the 1/2 times the numerator, minus the numerator, 8 r squared y minus 16 x squared y minus 8y cubed times the derivative of the denominator. And so bring down the exponent 1/2. Rewrite what's inside the power of 1 less times the derivative of what's inside, all divided by the denominator squared. Okay, let's just leave it like that. Okay. Actually, maybe I'll just evaluate it at this second. And so this is the partial, second partial. Please expect the mixed partial yx. At r over rad 3, r over rad 3. So this is going to equal 8. If you square this, you get an r squared over 3 minus 16 r squared over 3 minus 24 r squared over 3 again. The r squared minus r squared over 3 minus r squared over 3 gives me an r squared over 3 minus 8. And actually, let's cancel at least the 2's here. Minus 8. And let's multiply the y inside. So minus 8 r squared. Then your y squared gives you r squared over 3 And so there are 3 minuses, so that's going to be a minus 16 x squared times y squared is r to the fourth over 9. Again, there are 3 negatives. And so they'll give you a minus 8. This will be a y to the fourth, so that's r to the fourth over 9 times, well, the r squared over 3 to the negative 1/2. All divided by r squared over 3. Okay. So this is going to equal so the mixed partial at the critical value, r over rad 3, r over rad 3 is equal to, let's factor out, you have r squared and then a r cubed This doesn't look like a minus 1/2 right now. Here, wait 1 second. Oh, I see. Okay, don't. So I can't go that far. Okay, so I'll just leave it like that. Okay, so this is equal to, let's factor out r cubed over 3 rad 3. So what remains is, well, 8 minus 16 minus 24, okay, minus sorry, this minus and this minus here and this minus here made a plus. So this should really be a plus here. So I have here r to the fourth, but I'm dividing by r squared to the negative 1/2. I'm multiplying by r squared to the negative 1/2. So that means I'm multiplying by r to the negative 1. So that means that all these in here are r cubes, which I factored out. And, oops. So this becomes dividing by 3 to the negative 1/2 is the same as multiplying by 3 to the 1/2. And so I'm multiplying by the square root of 3. And so 9, the square root of 3 divided by 9 is dividing by 3 square root of 3. So this just becomes 24 minus 16 minus 8, all divided by, well, r squared over 3. So that's multiplied by 3. I don't know how to denote that. Okay. So if I do that, a whole bunch of things, well, some things will cancel. So these cancel. Two of these cancel. So that just gives you an R. 16 plus 8 is 24. So the 24 minus 16 minus 8 cancels. And so I get, oops, 1 second. So I get that this mixed partial is, well, 8 minus 16 is negative 8, minus 24 is a negative 32, R over rad 3. Okay. And let's do the other mixed partial. Of xy. I did yx. So let's do xy. So let's do that. So take the partial of y. Let me look at that for 1 second just to be sure that I have it here correctly. Let me copy that. And that's that next one. Okay. 1 second. Let's get it back. Control. Let's get back control. Okay, let's get another page. Okay. So let's take the partial. And so I get 8r squared minus 16x squared. That was an error. Minus 24x squared minus 16y squared. So again, I'm using the quotient rule times the denominator minus the numerator. The numerator times the derivative of the denominator. Then we bring down the exponent. Rewrite the denominator. The power 1 less times the derivative of what's inside, all divided by the denominator squared. Actually, it was better if I simplified it slightly before I did this. So This is equal to 8r squared minus 24x squared minus 16y squared. Multiplying and dividing by r squared minus x squared minus y squared to the 1/2. Those are going to cancel, so that's a minus, that becomes a plus. These cancel, so this is an 8. Don't know why I need a parentheses. R squared minus 8 x to the 4th minus 16 x squared y squared, all divided by r squared minus x squared minus y squared to the 3/2. Okay. So now, let's keep this here for a second because I'll need it. Now let's evaluate at the critical number. Let's see if I can, oh, no. So r over rad 3, r over rad 3. Okay, so let's plug that in. So you get 8. Okay, let's control back. So I get 8 r squared minus 24. X squared is r squared over 3. So those are going to cancel. Minus 16 r squared over 3. Again, this will be an r squared over 3 plus 8. That'll be r squared over 3 times r squared minus 8 r to the 4th over 9 minus 16 r to the 4th over 9. I need more room because that doesn't allow me to write in that location. Okay, come on, get back control. There it is. Okay, so let me move this. R squared over 3. R to the, let me just check. I think that was r to the 4th over 9. That was an r to the 4th over 9. All divided by, this was an r squared over 3 to the 3/2. Okay. So this mixed partial, hopefully actually this mixed partial will be the same as the other mixed partial, is equal to, so I'm evaluating here at the critical number. Okay. Okay, so you get here that these are both 8r squared, so these cancel. So you get and this is r to the 4th for 9. Okay, so those don't cancel. So now, let's factor out r to the 4th over 9. Okay. So I get here minus 16 plus 24 minus 8 minus 16 over, r squared to the 3/2 is r cubed. And I'm dividing by 3 to 3/2, same as multiplying by 3 to the 3/2. You can leave it like that. So cancels all but one r. Cancels, and you get a 3. So I finally get that this mixed partial at this critical number is equal to 24 minus 24 cancels, minus 16, really, r rad 3 over 3. It's a minus 32, okay. Well, but let me just see if I made a mistake. I made a mistake right there. From this line to this line, that was r squared. That was just an r squared. Okay, that was an r squared, which means if I multiply by 3, that becomes 24. Which means this became negative 16. R. Okay, so sorry about that, which means that they're the same thing. Okay, good. That was a typo. Okay, and now let's do the second partial. Respect to v, of v respect to r. Okay, so let's do this. So for numerator, 0, 0, minus, so again, the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. So bring down the exponent, rewrite what's inside to the power of 1 less, all times the derivative of what's inside, all divided by the denominator squared. These cancel. And so this is equal to, so slightly simplify, multiply and divide by r squared minus y squared to the 1/2. So you get a minus 32xy times r squared minus x squared minus y squared. Minus and minus become a plus 8xy r squared minus 8x cubed y minus 16x y cubed all over r squared minus x squared minus y squared to the 3/2. Okay, so we're almost done, but I think I just want one more page, just to be sure. And so this is equal to, let's evaluate at the critical number. r over rad 3, r over rad 3. So this becomes negative 32. If you multiply that together, that's r squared over 3. And this r squared minus x squared minus y squared is r squared over 3 as before, plus 8. R to the r squared over 3 times r squared minus 8. This is something to the fourth, so that'll be an r to the fourth over 9. This is also an r to the fourth over 9. And this is r squared over 3 to the 3 halves. Okay, so lastly, okay, let's evaluate this. Let's evaluate this, okay. And r over rad 3, r over rad 3. Factor out r to the fourth over 9. What remains is negative 32 plus 24 minus 8 minus 16 over r squared to 3 halves is r cubed. Dividing by 3 to the 3 halves is multiplying by 3 to the 3 halves. And so cancel out 3 of these and 3 of these. And so I get oops. So I get the following. So this will be an R. Let's see, this gives you 24 minus 24, that's 0. So this is a negative 32 R over rad 3. Okay, so finally the Hessian. Let's do H. And let's actually, well, let's write it as a matrix 1, 2, 2. Okay, so the partial with respect to x. Oh, okay, we'll write it that way because then they'll cancel. Minus 32r over rad 3. Minus 32r rad 3. Okay. And then the other partial, and they're both the same. They're both minus 16r over rad 3s. If I can grab one. Okay, there it is. They're both of this form. Okay, come on. Just don't freeze totally. Oh, I have to get rid of this guy anyway to clean it up. Minus 16r over rad 3. Minus 16r over rad 3. Oh, wait. Minus 16r over rad 3. Yep, they're both the same. Minus 16r over rad 3. Minus 16r. I did 1 as rad 3 over 3. and the other was minus 32. Don't know why I keep alternating when I rationalized and when I don't rationalize denominator. Okay, so first, so now let's finish off the second derivative test. So I noticed that at the critical number, this was negative over red 3. Keep writing it the wrong way. That's equal to a minus 32r red 3, which is less than 0. And so now we'll just do this because this was almost done. So now let's find the determinant. So it's a minus 32r rad 3 times minus 32r. I'll do the rad 3 in the denominator because it'll just make the calculation easier. Wasn't there a 3 then? Okay. Minus 16r over rad 3 and minus 16r rad 3 over 3. Okay, so this is equal to 32 times 32. The rad 3's cancel, so let me just do that. And so this is 1,024 r squared. The minuses cancel, and the rad 3's cancel. So you get 16 squared, 256. And then we just check, was that rad 3 really, was that 3 really in the denominator? Okay, that 3 was there. Oh. And let's see, rad 3, okay, those. I guess here, that would be correct, okay. It would be over 3, okay. So minus 256 over 3 r squared. So it's going to be some positive number. So 1,056 minus the 256 over 3 will give you, multiply that by 3. So that's 2,912 over 3 r squared. It's greater than 0. Okay, so since it's greater than 0, that means that both of the all the partials are curling in the same direction, and they're all curling down. So therefore, we're at a maximum. And so we're at a maximum. So, and that's what we wanted. And so we're at a maximum. Let me quickly go over. I could have also done this using Lagrange multipliers. The algebra is a little bit more difficult, but I don't have to make as many assumptions. Okay, so so the maximum is when x is equal to r over rad 3, y equal r over rad 3, and z equals r over rad 3. And so the dimensions of your box is 2 r over rad 3. So 2r over rad 3 by 2r over rad 3 by 2r over rad 3 is your maximum box. The dimensions of your maximal box. Okay, so suppose I wanted to do Lagrange multipliers. So again, we're maximizing the same quantity. So we're maximizing v equaling 8xyz, subject to the same condition, x squared plus y squared plus z squared equals r squared. So let's subtract r squared from both sides. So I just get x squared plus y squared plus z squared equals r squared. So let's form the Lagrange function, this Lagrangian. And so f of, and sometimes we call it L, of x, y, z, lambda. Why didn't I call it? F of lambda x, y, z. Let's call it that, having the lambda first. And so the partial of f respect to lambda is just, well, minus 1 times x squared plus y squared plus z squared minus r squared. The partial respect to x is 8yz minus lambda times the derivative of what's inside, 2x. The partial of f respect to y, well, is just 8xz minus y times the derivative of what's inside, 2y. The partial of f respect to z is just 8xy minus lambda times the partial of what's inside with respect to z, 2z. So if I want to find the critical number, I set each of these equal to 0. This is defined everywhere, so I don't have to worry about when this is not defined. So I set these equal to 0 and solve for x, for lambda, x, y, and z. And so if I take this set equal to 0, multiply by y, I get 8y squared z minus 2 lambda xy is 0. If I take this set equal to 0, multiply by negative x, negative 8x squared z plus 2 lambda xy equaling 0, and add, well, the 2 lambda xy's cancel, and you just get 8y squared z minus 8x squared z is 0. I can factor out an 8 and a z. What remains in the middle after I factored is y squared minus x squared. So I get that either 8x is 0, the 8z is 0, and so z is 0, or y is equal, y minus, y squared minus x squared is 0. We'll see that this is going to give us a contradiction. Will not be a maximal. This function will not be maximal at z equals 0. So similarly, so I've gotten to this point. Similarly, I can multiply this by z and this by y. Then if I add, by minus y. Then if I add, these cancel, and you get, again, factoring out your 8x. Z squared minus y squared is 0. So you get either x is 0 or y squared minus z squared is 0. Lastly, you can multiply by z and then x. So you can multiply, I forget which one, that one. This one by z and then by x. My negative x. Add, so these cancel. Factor out 8y. So what remains is y squared minus z squared. Set each equal to 0. And so y is 0 or x squared is z squared. First, you suppose lambda is not 0. Then, if x equals 0, then y is 0 and z is 0. But then 0 squared plus 0 squared plus 0 squared minus r squared has to be 0. I'm going to assume that r is not 0. So that's a contradiction. Similarly, if y is 0, then this says that x is 0. So if, let's say, x is 0 and y is, and lambda is not 0, then that says that y must be 0. And then this being 0 says that if lambda is not 0, z is 0. And so using these, we get a contradiction that r squared has to be 0 if either x, y, or z is 0. Okay. So we have that x, y, and z can't be 0. And so from the above, we have that x squared, y squared, and z squared are all the same. So let's just call them all x squared. And so I get that 3x squared is r squared. So x is equal to plus or minus r over rad 3, y is plus or minus r over rad 3, z is plus or minus r over rad 3. Okay, so now let's look at this Hessian for this Lagrange function. And so let's take all the second partials. So let's take the partial of f with respect to lambda. Well, we can see that this is going to be, there's no lambda here, so that's going to be 0. If you take the partial with respect to x, you get minus 2x with respect to y, minus 2y, z, minus 2z. And actually, you'll get by well, it turns out that the mixed partials are actually continuous. So this is actually C2, this function. So the mixed partials will be the same. So none of these partials are all that difficult to, they're all very nice to figure out. So if I look at this Hessian, and let's actually look at the determinant of this Hessian, I'm going to actually have to figure out well, actually, let's write it as a, and so if I plug in for each of these, I get the following bordered Hessian matrix. So let's first look at the determinant of this 4x4 matrix. Okay. So I guess let's expand along this. Doesn't really matter which way you do it. Along this first row. And so you get 0, so that doesn't give you anything, minus a negative 2x, so it's a plus 2x. Get rid of this column in this row, so you get this, minus, so it's plus minus plus, so plus a negative 2y. Get rid of this column in this row to get the next determinant. Plus, minus, plus, minus. So minus a negative gives you plus 2z. Get rid of this column in this row, so you just get the determinant of this. And so, take the determinant of this, minus 2y times the determinant of this, plus 2z times that determinant. Multiply in your 2x minus 2y and 2z inside the parentheses. And so then simplify. You notice that there are things in common you can factor out, such as a 16. Then use some of the above conditions. You had that 4zy minus xz, lambda x was 0. And so you actually had these 3 conditions from when the first partials, when the gradient was 0. So if you plug that in, then you'll get rid of the lambdas. And so then you just come out with this, knowing that x squared, y squared, and z squared is r squared over 3. So it should look pretty familiar. Each of these will simplify, just like what we did in the previous case above. And so you get that this is equal to some negative number. Okay, so I got that the largest of those minors was negative. Okay. Then take the next inner minor. Simplify, use the above facts as before to get the fact that x squared, y squared, and z squared was, no. And so then you simplify this. And so I then get this term here. Well, if this is greater than 0, then we're at a maximum. If it's less than 0, we're at a minimum. So to get a maximum, all these must be multiplied out to be greater than 0. And so